The rate at various partial pressures was given, and supposedly this equation will fit the data. The problem is we don't know K, both the rate constant we don't know K, the rate constant, or this big K, which is an absorption factor. You get this type of rate equation frequently in heterogeneously catalyzed reactions, solid catalysts, because of surface adsorption. Now, first off, what are the units? Well, the rate was given in units moles per second per cubic meter. And the partial pressure is given in atmospheres. This was specified in the problem. Well, within a term like this, the units here have to cancel because we have a 1 here. So the whole term here has to be unitless. So if the partial pressure of A is given in atmospheres, then K has to have units that will cancel that out, or atmospheres to the -1. Then the right-hand side of the equation has to have the same units as the left-hand side. So since this denominator here is unitless, then the numerator has to have the units moles per second per cubic meter. Well, the right-hand side also has atmospheres, and so the value of K has to then carry these units and cancel out the atmospheres of the partial pressure. So little k, the rate constant, has to then have units moles per second per cubic meter per atmosphere. Well, now that we've established the units for the rate constants and the large K, which is an absorption term, how do we express this equation in a linear form? Well, whenever you see a summation in the denominator, as you see on the right-hand side, one of the first things to try is to flip the equation over. So we'll have 1 over the rate is equal to 1 plus K PA to the 0.5, and this is divided by K PA. Now, whenever you see a summation, as you do here, to some power, we want to get rid of that. If it was a squared term, we would take the square root. If it's a square root term, we take a square. So we can then square both sides of the equation. Before I do that, and this is optional, I'm going to move the partial pressure from the denominator here over to the numerator here, just by multiplying through by the partial pressure. So we will have then a partial pressure over the rate is equal to 1 plus kPa to the 0.5 over the partial over k. Now I square both sides, and so I get PA over minus RA, and square that. This is equal then to 1 over K squared plus K PA over K squared. Now this actually is a linear form. If I plot this term here as on my y-axis versus the partial pressure on my x-axis, then this will be the slope and this will be the intercept. Note that you cannot have one of these constants here You can't have these in the term that you are plotting because you don't know their values. Likewise, you can't have one of your variables that you're measuring in the slope or the intercept because they're changing, and the slope and the intercept can't change. So what we want to do then is plot the left-hand side here, which I've marked y, on the y-axis, and the partial pressure on the x-axis. That should give us a straight line. Once we've calculated the partial pressure divided by the rate and then squared that, we can plot that versus the partial pressure, and you'll have to look at my solution to see a neat copy of this, but basically we have a graph that will have the partial pressure, and we want to include the units, atmospheres, versus the y-axis, which would be the the partial pressure over the rate, that's the opposite of, I guess, squared. And I would also include the units here. You'll see that they're kind of complicated in the solution. Now, in addition to this, we'll need to mark the axis, and what we want to do is use the full range of the graph if we can. Use as much real estate as your data will allow. And so I will mark this from 0 to 2, and I have some values in between, so I have 2.0. And on the y-axis, I went from 0 to 3. And this resulted in a straight line. The slope was so the slope was equal to big K over little k squared, and it is the rise over the run. Best to use the full extremes of the data here, and it turned out to be 1.25. We can't calculate K or big K or little k independently yet, but the intercept was 1 over k squared, and it is found here, and it's roughly 0.25. So when you calculate k, then I'll write this over here. K, the rate constant, then is 2, and the large K then turns out to be 5. And the data do indeed plot as a straight line, which verifies that this is an equation that does fit the data.